So Lydia and Mahbod will be talking about from two papers, from robustness to privacy and back, and robustness implies privacy in statistical estimation. So I think we're starting with Lydia. Thanks.
Thank you so much. So this is a joint talk about our papers that study and utilize the connection between differential privacy and robustness to data corruptions. One paper is by Hilal, Jonathan Ullman, and myself, which is work I did at Northeastern. And the other is by Sam Hopkins, Gautam, Kamath, Mahbod, Majid, who will present with me, and Shyam, Narayanan. So we study the general setting of statistical estimation, where we draw NIAD data points from a distribution D. We give them to our algorithm A, and we wanted to return an estimate of some parameter mu of the distribution D. And so the first thing we want is for the estimate to be accurate with high probability with respect to the distribution D. But two very common desiderata that we ask of these learning algorithms is one, differential privacy, that asks that we do not leak too much information about the sample X through this output. And the other is robustness, which asks that we're still accurate even under data corruptions or model misspecifications. So let's define these two a bit more formally. I'll skip the proper definition, but I'll point out to the fact, the thing to remember is that to separate the two notions a bit, that differential privacy is defined on worst case arbitrary pairs of data sets that differ on a single point. On the other hand, robustness asks something slightly different. It says, if you draw a sample from population D, even if you corrupt an eta fraction of points in this sample, then the algorithm should still be accurate. So more formally, an algorithm A is eta robust with accuracy alpha of eta if given a sample they're both formalizing the fact that the output of the algorithm should be insensitive to changes in its input. But they've mostly had separate bodies of work. So more concretely, what we know is the first paper that formalized their connection more was work in late 2009, who, among other things, said that epsilon differentially private algorithms are also inherently robust to a 1/epsilon fraction of corruptions. So differential privacy implies some level of robustness. Now, in the other direction, the connection was less clear, but we did observe that in recent years, a lot of the papers that ended up having an optimal differentially private estimator for some statistical inference problem were inspired or based on the equivalent robust estimator for that problem. So you start from the robust estimator for the problem and you try to have a private version of that estimator. So the question is, can we do this more generally? Can we always have a differentially private estimator starting from a robust estimator? And this is exactly what both our papers did. We came up with a black box transformation from any robust algorithm to a differentially private one. So a bit more formally, given a distribution D with a parameter mu that lives in a d-dimensional ball of radius r that we want to estimate, if A robust is an eta robust estimator with accuracy alpha of eta, then we can always construct an epsilon differentially private estimator. And moreover, the accuracy of the differentially private estimator will be the same as the accuracy of the robust estimator for a prescribed number of corruptions. So the accuracy of the private estimator will be the same as the robust estimators for d log r over epsilon n fraction of corruptions, and that is a rough bound for the purposes of simplicity. Okay, so the main idea behind this is to use the inverse sensitivity mechanism that on a high level returns a private estimate that is close to what the robust algorithm would output on that input. And this is essentially using the exponential mechanism over the space of parameters with a score function or a negative score function. That is the score of a point mu mu hat with respect to dataset X is the minimum number of points you need to change in order for the output of the robust algorithm on the modified dataset to be close to mu hat. So this is the score function. And by this fairly simple algorithm, we get this result. And if we modified it a little bit and use a truncated version of the inverse sensitivity mechanism with the proposed test release framework, we get an epsilon delta estimator instead, who doesn't suffer from this log R dependence and instead has the plus log 1 over delta term here, which is what you'd expect. So what our paper decided to do with this information is formalize a bit further the connection between robustness and privacy. So we proved that epsilon differential privacy and robustness up to log n over epsilon n fraction of corruptions are equivalent for low dimensional tasks. So that means that for tasks where the dimension is roughly a constant, under some natural assumptions on the non-private error of the task, the minimax error of satisfying epsilon dp, so that means the minimum error that any epsilon dp algorithm could have for a specific family of distributions and inference task, is the same up to constants to the minimax error of satisfying eta robustness for eta equals to this log n over epsilon n term. So the cost of satisfying epsilon dp and robustness up to this level of corruptions is roughly the same in terms of error. And the second thing we can tell is that this transformation for low dimensional tasks is actually optimal. So that means that we can always instantiate this transformation so that it gives us an epsilon differentially private algorithm that has optimal error for low dimensional tasks. So you might ask, okay, how do the differentially private algorithms that we get fare in high dimensional tasks? And Mahbod will tell you.
Thanks. So the reduction that Lydia just already described already gives us near optimal private estimators for many tasks in high dimensional statistics, including Gaussian mean and covariance estimation, sub-Gaussian PCA, Gaussian linear regression, and its sparse counterpart. But one major drawback of this reduction is that it is often going to be computationally inefficient. In our work, we focus on coming up with efficient implementations of this reduction. Specifically, we build on the soft squares exponential mechanism that existed in a previous work. The idea is to use soft squares-based robust algorithms in order to design private algorithms. But one major drawback of this soft squares exponential mechanism, its original format, was that it required convex score functions. This worked well for the case of mean estimation under bounded second moments, but it does not generalize well to other more generic soft squares-based robust algorithms. In our work, the nice thing is still is that the score function is not going to be convex, but it is going to be quasi-convex for these more generic SOS-based robust algorithms. So in our work, we design efficient and private samplers for soft squares-based algorithms for soft squares-based algorithms that are that lead to quasi-convex score functions. And in order to do so, we use convex body sampling techniques. So overall, we show that this black box reduction can be implemented in polynomial time for robust algorithms based on SOS. As one application, we apply this to the problem of mean estimation for sub-Gaussian distributions. Specifically, if you have a sub-Gaussian distribution with mean mu and identity covariance, and you take n eta corrupted samples from it, and then you can learn the mean mu up to error alpha plus O of eta using the following sample complexities. The first term here is going to be the over alpha epsilon. Alpha squared is going to be your non-private term. The second term in both cases is going to be the cost of fine estimation. The last term in pure DP is going to be the cost of coarse estimation. And in going from pure DP to approx DP, you would be able to avoid the term for coarse estimation, and instead you would need to pay log 1 over delta. Similarly, you can apply the same techniques to learning high dimensional Gaussians. Specifically, if you have a Gaussian distribution with mean mu and sigma covariance, and you want to learn it in TV distance, you can do so using n eta corrupted samples, and you can learn it with error alpha plus of eta using the following sample complexities. Again, the first term is going to be your non-private cost in both cases. The second term is going to be the cost of fine estimation, d squared over alpha epsilon. The last two terms in pure DP are going to be the cost of coarse estimation for covariance and the mean respectively. And in order to go from pure DP to approx DP, you would be able to avoid the cost for coarse estimation. So you would be paying log 1 or delta instead of the log kappa and log r terms. Okay. So in conclusion, in our two works, we give a black box reduction from privacy to robustness. Lydia's work focuses on establishing an equivalence between robustness and privacy for low-dimensional tasks. In our work, we focus on designing efficient implementations, polynomial time implementations for the same reduction, specifically for some squares-based robust algorithms. And we apply this to the problem of Gaussian mean and covariance estimation, and we give the first private and efficient and optimal algorithm for this problem. I should also mention that there is a concurrent work with our paper by Alabiko, Theritan, Kala, Venkat, and Zhang, who also solve a similar problem, but with a focus on the ambient dimension D. So that they are going to be optimal in the ambient dimension, but they are not going to be optimal in other parameters, and our work is going to be optimal in all parameters. Some open questions for future work may include coming up with faster or practical implementations of this reduction, because the efficient reduction that I described, it is going to be very slow, and it's not going to be practical. And also maybe we can apply similar techniques to other problems in private algorithm design as well. Okay, thank you.
Time for questions. Do you have any questions from speakers?
Repeat the question.
Yeah, can you? Oh, I was not able to hear. I was hoping.
What is the question? Maybe.
I did not catch the question. Sorry.
Is the question for the robustness to differential privacy reduction? Like, you mean? Sorry. Which side does this go to? Okay, sorry. The question is this reduction related to group privacy? But I'm not sure I got which side of the reduction, like the private. So definitely it's, you use the same thing as group privacy when you say that any robust algorithm is also differentially any differentially private algorithm is also robust to a 1 over epsilon corrupted points. So yeah, it's like group privacy. You're saying these things at worst case are going to differ in 1 over epsilon points. And so the privacy guarantees, yeah, it's a key thing of the proof, yeah. So you're right that group privacy is the thing you use to prove that differentially private estimators are also robust to changing, corrupting 1 over epsilon points. I'm not sure about the other direction. In the other direction, it is somewhat connected, but it's important that the estimator is robust, and in these, even if you change these points, it's staying within a close range of the true parameter. But yes, it's still roughly close. Yeah. Maybe we could take it apart. Yeah.
So you talk about small dimension versus large dimension. I was just wondering if you had the opportunity to look at this empirically. Do you know about where that line is, where it starts to become practical? It becomes a large dimension.
You mean for practical algorithms? Yes. I think it's going to be practical even in very low dimensions. Even like I think 5, even it's going to be pretty slow. Yeah.
Okay, the question was, is it, have you just tested it empirically so that you can tell if when it starts being impractical, even for high dimensions, but Mahbod said that even for 5.
I think even for very small d, it's going to be impractical.
Working in synthetic data, we watched batch algorithms playing around.
Okay, let's thank